Why? What? Why is the metronome on? That's garbage. Don't care about that. I don't need to be narrating this video in 4/4 time. Alright, so in this lecture, I'm going to be talking about phasors. A phasor is just a complex number that represents amplitude and phase of a sinusoid. You'll notice that the video here is not quite as well edited as I typically prefer, and the reason for that is that I need to do a little bit of online instruction right now, and it takes a really long time to get everything edited up nicely. So I'm sorry for that, but we're going to press on anyway. Alright, so let's recall imaginary numbers, and we are going to use, instead of I, many of you probably have seen I as the complex number, imaginary number prefix, the square root of -1 in your math classes. But in circuits, we use J. And the reason we use J, well, my anecdotal reason we use J is that I is already taken in circuits. We use I to represent current, so we can't use I, and so we just use the next best thing, which is J. So if this is true, a complex number can be written as Z, let's call that my complex number, which is X plus JY, where X is the real part and Y is the imaginary part. This form that I just wrote out is what I call rectangular form. It turns out that I can also write these in polar form. And in polar form, I would write Z as some radius with angle phi, which is equal to, can be also written in an exponential form, r e to the j phi. To summarize this, I've got Z equals X plus JY, that's my rectangular form. It's also equal to r angle phi, which is the polar form, and I also have r e to the j phi, that's what I call exponential form. Now, how do I convert between these? That's the next question. And what I should do is start with a nice happy right triangle. Let's say this is my right triangle. And R represents the radius. X and Y are the legs, and phi is the angle here. And if I plot this on a plane, I make the real part corresponding with the horizontal axis, and the imaginary part corresponding with the y-axis, the vertical axis. And so this representation using rectangular, polar, or exponential form allows me to capture the entire area of that plane by defining those values. So let's start with how I get X if I'm given R and phi. X is equal to R cosine of phi, because X is the adjacent, and I'm sure you all remember SOHCAHTOA or something similar to that. So cosine is adjacent over hypotenuse. So X is R cosine phi, which means Y is equal to R sine of phi. On the other hand, r, if I have x and y, I know r is the square root of x squared plus y squared, thanks to Pythagorean's theorem. And then phi is somewhat difficult. Phi depends on which quadrant I'm in on the complex plane. So I've got 1, 2, 3, and 4. So if I'm in the right-hand quadrant, let me denote that with a little bit of color here. If I'm in the right-hand quadrant, in other words, if the real part x is greater than 0, then phi is equal to the inverse tangent of y divided by x. All right, we're working in degrees here, so that's what we have. On the other hand, if we're in quadrants 2 or 3, so we'll put those over here. If we're in quadrants 2 or 3, here's the thing. If I take the inverse tangent, it's really defined between plus and minus 90 degrees. So let's say that I'm located, so one way to do this is say, all right, I've got plus x and plus y. This is plus x and minus y. I've got minus x and plus y, and minus x and minus y. So if I use this same equation of inverse tangent of y over x, things in quadrant 3 will look like things in quadrant 1 because the negative signs will cancel, and things in quadrant 2 will look like they belong in quadrant 4. So I need to actually apply an extra piece to this. So if x is less than 0, how I'm going to handle it is I'm going to say that phi is the inverse tangent of y over x plus 180 degrees. And then I'm done, and I have good conversions. So normally I would try to box this up. I can't do that very neatly because I didn't plan very well, but we're going to go ahead and work with that. So what we need to practice today is understanding how we might do operations with these numbers. So to do operations, and by operations I mean things like add, subtract, multiply, divide. Often we will add and subtract in rectangular form, and we will multiply and divide in polar form. So let's practice this a little bit. Let's suppose that I've got complex numbers z1 is equal to x1 plus jy1, and z2, which is x2 plus jy2. And so z1 plus z2 is just x1 plus x2 plus j times y1 plus y2. That's pretty easy. Subtraction works the same way. z1 minus z2 is equal to x1 minus x2 plus j y1 minus y2. If we also represent z1 and z2 using polar form, so I'll add that in here, r1 angle phi 1, and this is r2 angle phi 2. If that's the case, then I'd say z1 times z2 is equal to r1 r2 angle phi 1 plus phi 2. If I have just a standard complex number z, which is r angle phi, 1 over z is equal to 1 over r angle negative phi. Couple more operations left. The square root of z is equal to the square root of r angle phi divided by 2. And then the last operation I want to do, which is particular to complex numbers and really important, is what I call the complex conjugate, which is z asterisk is equal to x minus jy if z is equal to x plus jy. So what am I doing? I'm flipping the negative part. Alternately, if I have r, if z star or z asterisk is r angle minus phi if z is equal to r angle phi. So the complex conjugate is taking that complex part and it's switching the sign. One happy result of the complex conjugate is that 1 over j is equal to negative j. To prove that to you, here's what I'll do. I've got 1 over j multiplied by negative j over negative j. Which is equal to negative j times negative j, which is equal to negative j over negative j squared. Well, I know that j is defined as the square root of minus 1, so j squared is minus 1. So this implies that 1 over j is equal to, I've got negative j over negative 1, which is equal to negative j. That's a nice, happy result. I used this already, but I'll just point it out. J squared is equal to negative 1. Whew. That's a lot of information so far. I don't know how long I've been recording. Let's see. We've been recording for 363 bars at 120 beats per minute. I guess we could calculate that out. I can't imagine that you're that interested in that if you are interested in learning about phasors. I'll leave this up just for a minute. Give your brain a hot minute of a break. And actually, I'm going to stop this recording and then start a new one just to make sure that I have good screen capture going. I don't know how I'm going to fill that space in video, but we'll find out here in a minute. All right. So the idea of phasors comes from Euler's identity. So I'm kind of I turned the page on my notes here. Let's make a kind of a hard shift from having something which is all about complex numbers. Let's make a hard shift into the main topic of today, which is the topic of phasors. So let's go ahead and do that. The idea of phasors arises as a result of Euler's identity. All right, I have had professors before call this Euler's identity. I'm not sure what a Euler is. It sounds like something around Christmas time. Maybe you make Yule logs, but gulags. Anyway, this is Euler's identity. Euler's identity tells me the following. It tells me that e to the plus or minus j phi can be written as cosine of phi plus or minus j sine of phi. Plus or minus. The cosine of phi then is equal to the real part of e to the j phi, and the sine of phi is equal to the imaginary part of e to the j phi. So let's say that I'm given v of t, and it's Vm cosine omega t plus phi. Now, because the real part of e to the j phi is cosine of phi, I could rewrite this as being the following. I could say v of t is equal to Vm times the real part of e to the j phi, except that I'm going to replace phi, which is the argument of Euler's identity, with what's actually in the cosine. So cosine of omega t plus phi is j omega t plus phi, and I'll put that in parentheses so you can see that. So it's the real part of that. So this is actually equal to Vm times the real part of e to the j omega t times e to the j phi. And what we're going to do to make this stick is that we're going to keep the part which we're calling Vm, the amplitude, and e to the j phi, and then ignore that part. And so what I'll do is I'll collect those things together and I'll call them V phasor. Depending on what textbook you use, you may see this as a bolded letter, but I can't write in bold, so I use a vector. In fact, it makes sense to call a phasor a vector because vectors are a magnitude and a direction, and I've got a magnitude and then an angle or direction here. So V phasor is going to be Vm e to the j phi. And this is the phasor representation of my signal V of t. It has a magnitude and a direction, so it's a vector. And so in general, we can represent voltages and currents by taking their amplitude and angle as long as they are in cosine form. Let me write that down. We can represent voltages and currents by phasors using the magnitude and angle as long as the signals are in cosine form. So one thing that we like to do with phasors is we like to represent them using a phasor diagram. So let's look at a little example of this. What I'm going to do is I'm going to define some V phasor, which is Vm angle phi, and then I'll say I is equal to Im, so I phasor is Im angle negative theta. And I can use a phasor diagram. And we already talked about this a little bit, but what I'm going to do is I'm going to put this on the complex plane. So I've got the real part, and I've got the imaginary part. And let's say I've got Vm here, or V phasor, which has Vm magnitude and angle phi. And then I've got Im for I phasor with angle negative theta. And if I consider this plane, what I'm going to say is that omega increases as I go around, and the angle increases. And so what we're going to say is that going up from this real axis is called leading, and going back here is called lagging. Now, these are actually terms where you're comparing things relative to each other, but a leading power factor would be something, or a leading signal would be something which has a positive angle, most likely between 0 and 180 degrees. So let's distinguish some important things here. First thing to notice is this, is that V of t, which is equal to Vm cosine omega t plus phi, is something that exists in the time domain. And Vm angle phi, which is my V phasor, this exists not in the time domain, but in the phasor domain, which is actually a frequency domain. And in fact, to make things work here, if I'm going to work with signals that are phasors, they must all have the same frequency. We'll talk about that a little bit more in a later lecture, or maybe even a little bit later on. So let's look at the sinusoid phasor transform. Vm cosine of omega t plus phi transforms to Vm angle phi. Not a shock. Vm sine omega t plus phi. For those of you who have seen information about sinusoids and how we represent them, I know that what I'm trying to do here is take a cosine and project it onto the sine axis. And typically I align the cosine, because of I know it's the real part, I align that with the real axis, and sine is down here. So if I want to move a cosine into looking like a sine, I've got to take minus 90 degrees. So it's going to be Vm angle phi minus 90 degrees. So there's my transform. If I start with a cosine, I can take Vm angle and then whatever phase angle I have. If I start with a sine, I need Vm angle, that phase angle, minus 90. There are a couple other important notes before we finish up, so let's leave that where you can see it. So some other important notes. So here's the first one. Something that is going to be useful when we start talking about capacitors and inductors. If I take the derivative of a signal in the time domain with respect to time and convert it to the phasor domain, I have j omega v. Any of you familiar with the Laplace domain, you could see that if you ignore initial conditions, j omega is equal to s. Similarly, the integral of v dt could be converted to v phasor over j omega. These things are very important for capacitors and inductors. Second important point is that v of t is the time domain. I said this in words before, but I'm going to write it down. V of t is the time domain. V phasor is the frequency domain. Third important point is that V of t is time dependent and V phasor is not. I'm going to pause right here and point out something that's really neat, and that is, since V is not time dependent, suddenly my circuit could look like, well, it could look like a DC circuit, because in a DC circuit, current and voltage are not time dependent, they are constant. So the reason we use phasors is to make a circuit with time varying signals appear to be time independent. All right, number 4, V of t is always real valued. But V phasor in general is complex. So what do I mean by that? Well, V of t is a real signal. It's something that we can measure. V phasor is a convenient mathematical tool that we use. So that is the big distinction between those. And then the last note here, which again I said verbally, phasors only work if all of the signals in the system are of the same frequencies. So they only work for signals of the same frequency. And that becomes really important when we talk about superposition in alternating current AC circuits here in a future lecture. All right, that's it for this lecture. Please let me know if you have any questions by posting in the comments or if you have a way of reaching out to me, you can do so. You can find me on Twitter at BDMcFerrin, and always send me a message on there if you have questions as well. All right, thanks for watching.